Okay, so today we'll continue our discussion of gases, which is chapter 10. So in the previous lecture, we talked about the properties of gases, the fact that gases can be compressed, they're compressible, whereas solids and liquids cannot be. And then we talked about a little bit about the nature of pressure. Pressure, turns out, is a very convenient method or idea for measuring the properties of gases because of the compressibility of gases. And we'll look at that in a little more detail today. But we said that essentially the pressure, which we'll use the symbol P, is equal to the force applied divided by the area, the surface area, right? So this is going to come into play when we start talking about this idea of the gas cylinder, which we already talked about in chapter 5 with thermochemistry. We said that we could do mechanical work if we compress a gas. Okay, so if we have a cylinder and we confine a gas to that cylinder, what we find, we'll talk more about this as we go into the kinetic molecular theory of gases. But what we find is that there's something called air pressure, which is due to the weight of the air. The atmosphere has a weight. We don't really think about it very often, but there's a weight to the atmosphere. The atmosphere is miles thick. And so even though there aren't very many molecules of air per given volume, take that over miles, you've got quite a bit of number of molecules. So they exert a pressure on surfaces in our skin, for example, as well as other things. Okay. So we're going to talk a little bit about pressure today. First step is to do some conversions, just very simple conversions. Okay. And so there are many different units of pressure that are used. We talked about the Pascal. And the symbol for the Pascal was a capital P with a lowercase a. Okay. We had the kilopascal, which is just a Pascal with a prefix in front of it, right? So K for kilo, Pascal. And then we had what we called the torr. Okay, the symbol for the torr is actually, technically it's called the torricelli, but no one calls it that. They're called torr. So the symbol is essentially the same as the name. We have millimeters of mercury. Which is written typically as mm for millimeters, and then Hg, the symbol for mercury. And then there's the bar, BAR. The abbreviation for bar is the same as the name of it. And there's the pounds per square inch. So you can see there's a lot of units here, right? Typically written as PSI or PSIG, depending on how it's measured. And I think that's, atmospheres, which is ATM. The abbreviation for atmosphere is ATM. So the ATM, I recommend just sort of starting with the ATM, with the atmosphere as your sort of baseline, which is, y'all kind of know what an atmosphere is, right? It's essentially atmospheric pressure. And it can vary a little bit, but essentially just use atmospheric pressure, okay? So I'm gonna write it as 1 ATM. And then I'm gonna write some conversions, okay? So the first conversion is pascals. So 1 atmosphere is equal to 1.01 times 10 to the 5 pascals. Okay, so Pascal is pretty small. There's a lot of pascals in 1 atmosphere. 1 atmosphere is equal to 101. I'm sorry, it's 1.03. Sorry, 1013. I see what I'm doing. I'm trying to do this from memory. Sometimes it's not a good idea. 1.013 times 10 to the 5. So 101.3 kPa, kilopascals, okay? So I just moved the decimal place over 3 places and got rid of the exponential notation. 1 atmosphere is equal to 14.7 psi. I don't think Alex has you do psi. The textbooks typically have you do psi. 1 atmosphere is equal to 760 torr. 1 atmosphere is equal to 760 millimeters of mercury. Okay, so the torr and the millimeter of mercury are the same thing. The torr is just typically what people call it, but it's measured. The way you measure millimeters of mercury is by just looking actually the height of a cylinder of mercury. And so it's 760 millimeters is 1 atmosphere, okay? And, you know, if we have a gas inside of a cylinder here, it could be greater than an atmosphere, it could be less than an atmosphere, it could be equal to 1 atmosphere. But atmospheric pressure is typically written as 1 atm, right? So that's your atmospheric pressure. And in a gas cylinder, we call that the external. External meaning outside, right? So it's the outside pressure is 1 atm, okay? If the piston is balanced, meaning the piston is not moving, it's just sort of sitting there, we call that equilibrium. If it's moving, it's not an equilibrium, or it's non-equilibrium. But if it's just sitting still, that means it's equilibrium. And what that means is the pressure inside, the pressure of the gas inside is equal to the external pressure. So we would call this equilibrium. You'll use that term a lot in the next course. Equilibrium is the case where the external pressure, the atmospheric pressure, is equal to the internal pressure. I'll just write this out, internal, all right? Okay, and that's important because essentially we do a lot of problems where we want those two pressures, where it's convenient to have those pressures be equal to each other, okay? So these are conversion factors. You know, you don't need to memorize them. It's useful to know a couple of them, like this one right here, PSI. This is common because, you know, if you're using a bicycle gauge or a gauge for your tire in your car, you're blowing, you know, you're inflating your tires. Typically in the US, they're done in PSI. So an atmosphere is 14.7 PSI. This one you do a lot. This conversion factor comes up a lot, atmospheres and torrs. So those are good to know, but you can just write these down, have them on a little card, and then you're set to go. So let me show you an example. Let's do a little conversion here. We're gonna do atmospheres in kilopascals, and then we'll do atmospheres in torr. Okay, so the first one is, it says, so this is interconverting, right? Interconverting means we're converting between one unit and another. And this one's atmospheres and kilopascals. Okay, so if we're going to do that, well, let's just write it down here. 1 atmosphere is equal to 101.3 kPa. It's actually 101.325, but I'm just going to keep it at 4 sig figs right here, okay? So it says in this problem that the partial pressure of nitrogen, the partial pressure, this is a term we'll talk about later, of nitrogen in the atmosphere is, I assume this is at sea level because it does depend what height you're at, 79.11 kPa, kilopascals. So what is the partial pressure in atmospheres? That's the question. So you've got in kPa, what is it in atmospheres? Here's our conversion factor here, right? After all the work that we've done in this course, these now suddenly don't seem so difficult, right? So you take the measurement you got, 79.11 kPa, and we do our conversion factor. We want to get atmospheres, so we're going to put the atmospheres in the numerator. And we're going to put the kPa in the denominator. kPa cancel, and now we'll have atmospheres, okay? Now, let's see how that works out. Actually, let's just go ahead and use this one right here. So 79.11 divided by 101.3, looks like it's 0.7809, 0.7809. Atmosphere. That sounds about right. So in general, people will say that the atmospheric pressure or the constitution of the atmosphere is it's around 79% nitrogen and 21% oxygen. And that's typically done by volume. And this is in pressure, so it's pretty close to it. It's around 78% nitrogen in terms of pressure units, okay? All right, so let's take a look at another one. The next one is we're going to interconvert atmospheres and torr. Okay, so in this one, it says the vapor pressure of water is 0.468 atmospheres. So at 80 degrees C, the vapor, we don't have to worry about what vapor pressure is or partial pressure yet. We'll get to that stuff, but it's just pressure. Is 0.468 atmospheres. Calculate this vapor pressure in torr and in millimeters of mercury. Okay, do it in both. All right. Not a big issue, right? Not particularly challenging because again, we have this conversion factor, which is 1 atmosphere is 760 torr. But then again, it's also the case that a torr is a millimeter of mercury. So this is also equal to 760 millimeters of mercury. Okay. So once you get one of them, you've got the other one too. So 0.468 atmosphere. We want to have it in torr, so we'll put the torr in the numerator. We'll put atmosphere in the denominator. So what do you got? 0.468 times 760. Yeah, times 0.468 times 760. And it looks like it's around 356. And then that would be torr. Okay. It's about a half an atmosphere. 0.468 is pretty close to 0.5, so it's about half an atmosphere. So half of 760 would be around 380, and that's, it's pretty close to that. And then again, once you've got this one, you know the number of millimeters of mercury because a torr is the same as a millimeter of mercury, and you've got that one too. So you got both of them. Okay. So for the ALEKS, those are the two types of conversions that you'll be doing. You'll be doing the atmospheres in kilopascals, atmospheres in torr. For those of you that are engineering majors, you'll want to practice a little bit about PSI, because PSI is also used. And in physics, you typically use kilopascals. So that one we already did. Okay. All right, pressure conversions. Now, let's talk about the gas laws. So this is the second section. It's called gas laws. So this is where we get into the sort of, the main chunk of this chapter is dealing with gas laws. So we're going to start with one called Boyle's law. Now, Boyle's law relates pressure and volume. Now, this, if you recall, is significant because when we talked about the gas cylinder in chapter 5, right, we said, wait a minute, there's this thing called work. And we said that work was equal to minus P delta V, right? So we have this piston here. We have a gas inside the cylinder. And we said if we compress the gas, we're doing work on the gas. If the gas expands, the gas is doing work on the piston, right? So that was mechanical work. Well, notice what we have here. P and V, P times V, right? It's delta V, but it's pressure times the volume, okay? So that's what we're talking about here. Now, the relationship we're going to look at is how one affects the other. Not work. We're not concerned about work right now. We're just doing pressure volume. So how does the pressure of a gas affect its volume? Gases are compressible. So if you push down on a gas, it will compress, right? So let's write that down. Pushing down. Now, let's be technical. When you're pushing down on something, you're applying a force, right? That's what pushing down is. You're applying a force. So pushing down on a gas compresses it. It compresses the gas. And so the way we would say that is that the volume decreases, right? If you push down on something, the volume is getting smaller. Another way of putting that is delta V is negative, right? If something gets smaller, the volume got smaller, so that change is negative. Okay. The opposite of that would be that a gas pushing up, pushing the piston up, okay? Piston, sorry, I'm misspelling piston, up, okay? Expands the gas. So if the gas pushes the piston up, the gas is expanding, right? And so we would say the volume increases. Or we could say delta V is positive, right? That's another way of putting it. Delta V is positive. So there's two cases here. Either the gas gets smaller, compression, or it gets bigger, expansion. And it's inversely related to the pressure. So what happens is the more you push down, the greater the pressure, the smaller the gas gets. If you relieve the pressure, if you quit pushing down, the gas will expand, right? That's essentially what's happening in equilibrium. When that piston, when that disc is not moving anymore, that means the pressure upward from the gas is equal to the pressure downward from the atmosphere. If those two are equal to each other, you're at equilibrium. So I'm going to write it in a couple of different ways. Typically, it's not done as delta V calculations with Boyle's law problems, although it could be. We could do a problem where we said, what's the change in volume or what's the change in pressure? Typically, it's done with an initial and a final state. And here's what Boyle's law says. This is all based on many, many experiments. The pressure of a gas, and again, we're just talking about gases here. The pressure of a gas times its volume appears to be constant. Okay, now there's some assumptions here. Here's the main assumption. The assumption is that the temperature is constant. Meaning it's not changing. If the temperature is changing, then all bets are off. We have to use a different relationship. But the pressure times the volume under the case of constant temperature, this is called isothermal. Isothermal means constant temperature. If we're under isothermal circumstances, then the pressure times the volume is constant. Okay? Very simple. So now we can write this in certain ways. So one way we could write it, I'm going to get rid of the x for times and just write P times V, is equal to a constant, C. Could write it that way, C for constant. Right? That, it turns out, can be useful, but it's typically not that useful. What's more useful is to say the following. If we have an initial situation, I for initial, and an initial volume, so the pressure, the initial pressure times the initial volume, if that's constant, then that means if we change one of them, so I'm going to change the initial pressure to a final pressure. I've now changed it. If that's true, then the volume has to change too. Okay, so keep in mind, if I change one of these, the other one has to change too, because the product has to be constant. You just try numbers, right? If I made P equals 1 and V equals 1, 1 times 1 equals 1. That 1 is the constant. If I change P to 2, well, 2 times 1 is no longer equal to 1, so it's no longer constant. So the constant is what's important. So if the pressure changes, the volume has to change too. So if P becomes 2, V would have to become 1/2, right? If 1 times 1 is equal to 1, then 2 times 1/2 would be equal to 1 as well. So the volume would have to change. So typically it's written this way. The initial pressure of a gas times its initial volume is equal to the final pressure of the gas times its final volume. So diagrammatically, let me show you a little diagram to kind of represent this. So you got all these little gas molecules in here, right? So there's some pressure. There's a pressure in there. And then there's a volume, right? The volume is the size. If you change the pressure, okay, so let's say the pressure is bigger, so I push down on it even harder. If you push down on it even harder, the volume is going to get smaller. So if P went up, you now have P final. V had to go down, and you've got V final, right? So volume is smaller if you're applying more pressure to the gas. So that's your Boyle's law right there. Pi Vi equals P final V final. It is sometimes written as P1 V1 equals P2 V2. Either way, you want to use initial final, IF. You want to use 1, 2 for second. You want to use AB. You want to use XY. It doesn't matter. Whatever the subscripts are, the pressure times the volume is a constant. So the initial is equal to the final. Okay? Doesn't mean the initial pressure is equal to the final pressure. It means the product of pressure times volume is constant. So let's take a look at an example. Very simple. Boyle's law is about as easy as it gets. Okay, in this question, this is called Understanding Boyle's Law. You got a cylinder. So they show you a picture of the cylinder with 10.0 liters of gas in a piston. The initial pressure is 182 kilopascals. So we're using kPa here. Now we push the gas down. To a final volume of 6.50 liters. Calculate final pressure. Pretty simple. Let's take a look. There's a picture here. Okay, so there's your piston. Your gas is in here, so we'll shade it in to show the gas in there. Okay, so your gas is inside there. So your volume, your initial volume is 10 liters. And your initial pressure is 182 kPa. And then they say they compress it down to 6.50 liters. So now the gas is down a little bit smaller, right? Not as big as it was. So there's your volume. So the final volume is 6.50 liters, and they just want to know the final pressure. Okay. So very simple. Whenever you see, it doesn't say it's a constant temperature, I guess. That's an interesting aspect of it. So it's only valid at constant pressure. So if they don't say anything, I'm sorry, constant temperature. If they don't say anything about the temperature, I guess you could just consider that it's constant. But Technically, they should have said it occurred at constant temperature. So we have our values. We're just going to find P final. So let me just take the equation. VI, I put P first. It doesn't matter whether you put P or V first, but PI times VI equals PF times VF, right? So we want to find the final pressure. So we divide both sides by V final. Right? V final, V final. And that gives you P final, right? So we want to take the initial pressure times the initial volume and then divide it by the final volume. So 182 kPa times the initial volume, which is 10 liters, and then divide that by our final volume, which is 6.50 kPa. And that's going to be our P final. Okay. So let's kind of think about it, right? The idea is that if the pressure goes up, the volume should go down. If the pressure goes down, the volume should go up, or the other way around. If the volume goes up, the pressure should go down. If the volume goes down, the pressure should go up. They're opposites of each other, right? It's called an inverse proportionality. So when we do this answer, we should get a higher pressure at the end, right? Because the volume went down, so the pressure should go up. So if we get something less than 182, then there's something wrong. We should get something greater than 182. And you can look at the numbers and see that'll happen. So it's 182 times 10 divided by 6.5, and you get 280. Let's do our analysis of units. Kilopascals divided by kilopascals, and we have liters. Oops, sorry. What did I just do? Oh, I see what I did. This was 6.5 liters. Okay, so 182, so that would be kilopascals. Oops. Oh, wow. Sorry. A technical glitch here for some reason. Okay, so liters are going to cancel, sorry. Or it's not kilopascals that cancel, it's liters that cancel. Okay, let me just charge this up and see if this works. Oops. Having a little problem with this pencil. Okay, so 280. All right. Let's see. So let's take a look at another one. Okay. I'm going to try to write this now. Oops. Oh dear. Okay, let's try a new one. So it's 280. I'm sorry. I'm just having a little problem with the pencil here. There we go. 280 kPa. Okay. All right, let's try a new one. All right, so for this one, this is called an application of Boyle's law. So in this one, they say that you have a marine biologist. Just hide that. You've got a marine biologist, and the marine biologist is preparing a deep sea submersible for a dive. Okay. And the sub stores breathing air under high pressure in a spherical air tank that measures 61.0 centimeters wide. So let me draw a little picture for you. So I don't know what this submersible looks like, but it's a submarine, right? So it should be sort of like a tube. And inside that tube, I guess we'll put a little area up here for our marine biologist to pilot this thing, right? So inside there, there's our propeller. We got a little spherical tank, right? There's a spherical tank inside this submarine, okay? And what they do is they say that that's where your air is. That's your air supply. Okay. So the air has a spherical tank that measures 61.0 centimeters wide. Okay, so that's the size of your tank. So what they're saying is this, the diameter, right? That's the diameter is 61.0 centimeters. And the biologist estimates that they will need 4,700 liters of air needed. Okay. Calculate the pressure to which this volume of air must be compressed to fit into the air tank. So calculate the pressure to which this air will need to be compressed in order to fit in the tank. All right, so here's the idea. There's an assumption in here. Well, one assumption, there's a couple assumptions. Let's write our assumptions down. Temperature is constant. There's nothing said about temperature. Doesn't say the temperature is changing. Doesn't say it's constant, but we'll assume that it is constant. Okay. If we don't have a constant temperature, we can't use Boyle's law. We have to use the ideal gas law. The second thing is not obvious, but when you think about it, it becomes obvious, which is in the submarine, the pressure of the air is going to be 1 atmosphere. Okay, it's going to be an atmosphere, right? Because when you breathe air, it should be at 1 atmosphere. So they ask you to write the answer in atmospheres. So write your answer in atmospheres. Now, I guess you could argue, well, maybe they don't really want to have the submarine at 1 atmosphere. Maybe they want to have it at 2 atmospheres, or maybe they want to have it at 0.9 atmospheres, whatever. We'll assume it's 1 atmosphere, because if you're breathing, it's easiest to breathe at the pressure that we're used to, which is 1 atmosphere. So what we have then is essentially we know the volume of the submarine, and that's 4,700 liters. And we know what pressure we need that air to be at, which is 1 atmosphere. So in the sub, we have pressure equals 1 atm and volume equals 4,700 liters. Okay, now here's what else we know. We know that that air is gonna get pushed into this tank, right? We need all that air to be in this tank. So the question then is, what's the pressure of the air in that tank before it fills up the submarine? Okay, that's essentially what we're looking at. So here's how we deal with it. Well, we say, look, if we know the size of the tank, that would be the volume of the tank. Okay, so for the tank, we would know that the volume is something. If we could figure out what that is, then we could figure out what the pressure of that tank is, the pressure of the gas, of the air in that tank, right? The problem is they don't give us the volume. They just give us the size, right? They just say, hey, it's 61 centimeters wide. So here's how you deal with that. To find the volume of a sphere, this is from your high school geometry, right? The area of a circle is pi r squared, right? Pi times the radius squared. The volume of a sphere is 4/3 times pi times the radius cubed. Okay, so the volume of the sphere is 4/3 times pi times the radius of the sphere cubed. They don't give us the radius, though. They give us the diameter. The size, or the width, is actually the diameter. So the radius would be 1/2 the diameter, right? Think about a circle, a sphere, it's the same thing. If you have a diameter, the radius is 1/2 of that, right? The radius is from the center to the circumference, right? So that's the radius right there. So radius is 1/2 d. So if the width, which is the diameter, is 61, this would be 1/2 times 61 centimeters. So that's what, 30.5 centimeters. So now you got your radius. Now, what you can do is you can ask yourself, well, what's a liter? And how does that rate relate? And there's a couple of different ways you can do this. What I would recommend doing is actually just finding the number of centimeters cubed and then converting that to liters. And the reason we can do that is that 1 centimeter cubed is equal to 1 milliliter, right? We have that. It's the same thing. A cc is a centimeter cubed, which is a milliliter. And then we know that 1 liter is 1,000 milliliters. Okay, so we have one of the volumes in liters. We don't know what the other volume is, but we can calculate it. So my recommendation would be calculate the volume in centimeters cubed, which is milliliters, and then convert it to liters. Okay, so let's try that. The volume of the sphere, the volume of the tank is 4/3 pi, and then we're going to take 30.5 centimeters and we're going to cube it, right? R cubed. And then that'll give us the volume in centimeters cubed. So got to use your scientific calculator here. 4 divided by 3, so that's 4/3 times pi times 30.5 raised to the 3rd power. Now some calculators have a cube function. This one does too. Okay, so there we go. So what do you get? You get this big number. You get 118,850 centimeters cubed, right? Pi doesn't have any units. 4/3 doesn't have any units, so it's just the volume. It's just the radius cubed, so centimeters cubed. But again, that a centimeter cubed is a milliliter. So the volume is also equal to 118,850 milliliters. So now you can convert that into liters because you have this relationship right here. So I'm going to take the milliliters and just say, hey, a liter is 1,000 milliliters. And that'll get rid of the milliliters. And now you got 118.85 liters. Now you got this number that's not so unreasonable, right? 118 or 119 liters. Originally, it was 4,700. That's, smaller. So that makes sense, right? You want the volume to be smaller on the inside than the volume of the entire submarine, right? You're storing your air in here. Okay, so now we've got our volume. And the question then, coming back to the original question, is calculate the pressure, right? Calculate the pressure to which this air needs to be in the tank in order to work out. So I'm going to write it this way. Pressure of the tank times volume of the tank is equal to pressure of the submarine times volume of the submarine. You can use IF for initial final or 1, 2, but you could also use subscripts like this, T for tank and so T for tank and then S for submarine, okay? We want to know the pressure inside the tank. So that would be PT. So we're going to divide both sides by V of the tank. Okay, V of the tank, there we go. So what do we have? We have pressure of the tank is equal to P of the submarine times V of the submarine divided by V of the tank. Okay, so P of the submarine is 1 atmosphere, right? The V of the submarine is big, right? 4,700 liters. V of the tank is 118.85. Okay, so liters will cancel and we'll get atmosphere, and it should be bigger, right? It should be bigger than 1 atmosphere, right? you wouldn't store in a tank atmosphere pressure less than 1 atm. You put a lot of it in there and then let it spread out. So the volume gets bigger, the pressure gets smaller. So a lot of sig figs I put in there, but we'll just round it to 3. So 1 atmosphere, I'm assuming 1 is exact. So 1 times 4,700 divided by 118.85. And then we're just going to round it to 3 sig figs because, well, the question said round it to 3, but it looks like you got 3 sig figs there. Okay. So it looks like it's 39.5. And that would be the volume of the, I'm sorry, the pressure of the tank. Okay. So if you take the air in the tank and you pressurize it, right? That's the term we would use. You pressurize it to 39.5 atmospheres in that small volume. That's enough air to fill up the entire submarine with an atmospheric pressure, 1 atm. And so if you think about it, really what you're doing when you put this air at high pressure, you're pressurizing the tank, is you're moving the molecules closer to each other, right? So when we say the volume of a gas gets smaller, it's compressing, really what's happening is the molecules are getting closer to each other. When a gas expands, like it did here, it expanded into the submarine, the molecules are getting further and further apart. That doesn't work with solids or liquids. Solids or liquids, if you take a rock and you throw it into a submarine, it doesn't spread out and take up the whole space. It just stays as a rock. So rocks and solids and liquids don't change their volumes. Okay. So there you go. So that one's a little more involved because you got to do a little bit of geometry. So if you get these kind of problems where they're giving you the size of something, you can say, hey, the volume of a sphere is 4/3 pi r cubed, where r is the radius, which is 1/2 the diameter, right? And the diameter is the width. If you get a cylinder, if they ever have you do a cylinder, the cylinder is pi r squared h. So the volume of the cylinder is pi r squared h. Okay. Yeah, where r is the radius, and again, 1/2 the diameter. H is the height of the cylinder. Okay, so let me show you a picture of that one. Okay, so a cylinder is essentially a stack of circles, right? That's what a cylinder is, an infinite number of circles that are infinitesimally thin. So what's the area of a circle? The area of a circle, there's your radius. The area of that circle is pi r squared, right? So then now you have this height. There's your height. So essentially, you just take the area of one circle, the area of the next circle, the area of the next circle, the area of the next circle, the area, and then you've got your volume, right? The volume would just be all that together. So the volume then is just the area of the circle times the height, okay? And then if you have a cube, it's relatively rare that we put a gas in a cube, but if you do, if you have a problem where they give you a cube, that's pretty simple, right? So you got, well, let's do it this way. Got your height. Well, let's use the lowercase. You got your height, you got your length, you got your width. So the volume of a cube is just the length times the width times the height. But in a cube, the length is equal to the width, which is equal to the height. So it's just equal to the length cubed. Okay. That one's pretty easy. But typically, you don't see problems with gases in a cube. You're more likely to see it in a cylinder or in a sphere. Okay. So let's take a look then at Charles's law. Okay. So this is called Charles. Sometimes people put the extra S. And this is volume temperature. Okay. So Boyle's law is the relationship between pressure and volume. Charles's law is the relationship, is the relationship between volume and temperature. Okay. So let me show you the relationship. It's a bit different. The relationship is that the volume divided by the temperature is equal to a constant. So just so that we're not using the same constant as we did with Boyle's law, I'll put a little subscript there, CC, where the little lowercase c just means Charles. So it's a different constant, but it is a constant. So notice it's not the product. It's not, V times T, it's V divided by T. Okay, so that's an important aspect. That leads to this relationship. V1 over T1 is equal to V2 over T2. Okay, and that's typically the way we write Charles's law. Okay, now one thing to talk about this. The temperature for this course and for pretty much any course you're going to use, with the exception of maybe engineering courses, we're going to use the Kelvin scale. Okay, the temperature in Kelvin is equal to the temperature in degrees Celsius plus 273.15. Typically, we round it to 273. It's up to you. Depends how many sig figs they give you for other things. If they give you, 4 or 5 sig figs for the other numbers, use the whole thing. But if they only give you 3 sig figs, you can usually round it to 273. Okay. Okay, so the reason we have to use the Kelvin scale is because the Celsius scale is just physically incorrect for these sorts of calculations. It leads to kind of ridiculous answers for certain calculations. Same thing with Fahrenheit. You can't use a Fahrenheit system for Charles's law. So if you think about it, what would happen if I put in 0 degrees Celsius, which is the freezing point of water? That's a possible temperature, right? Air doesn't freeze at 0 degrees Celsius, right? Air is still a gas at the freezing point of water. But if you put 0 in for your temperature, you're going to get an undefined answer, right? If I put in the initial temperature is 0, V divided by 0 is undefined. There's no result. Same thing with negative, right? We can have negative temperatures in the Celsius scale. So if I say the temperature is minus 5 degrees C, well, volume divided by -5 would give me a negative, right? Which would mean that the final temperature would have to be negative, or the final volume would have to be negative. Well, that doesn't make any sense. So we can't use the Celsius scale. We can't use the Fahrenheit scale because both of them have negatives and they both have zeros. So we use the Kelvin scale. And so the Kelvin scale doesn't have any negative values. It doesn't even really have 0. In theory, you might be able to reach 0, but in practice, you can't. So Kelvin's are always positive values. Okay. All right, so we'll use that. You just add 273. So typically the questions you're going to get, they're going to give you the temperature in Celsius, but you have to convert it to Kelvin. That's just a given for gas law problems. So if you're doing any problem with gases, make sure the temperature is converted into Kelvin if that happens. Now, there's an assumption with this one that's not generally stated. Sometimes it is, though. And the assumption here, constant pressure. Okay, so just like with Boyle's law, the assumption is constant temperature. With Charles's law, the assumption is constant pressure. Okay, so looking at Alex, actually, for the first Alex problem, they actually do tell you it said exactly, it stays constant. So they put that in there. So let's take a look at using Charles's law. So in this example here, they have a weather balloon. Weather balloons are cool. If you go on YouTube and look up weather balloons, people do neat things. They take a weather balloon, tie a digital camera to it, and put a GPS tracker, and then just let it go, and it'll go like miles up into the atmosphere, like 20, 30, 40 miles up to the edge of space. And then what you do is eventually it pops, the balloon will pop, it'll burst, and it'll come back down. And if you got the GPS tracker, you can go find it, drive over to it. And then you've got like a little video of like going up practically to the edge of space. It's kind of cool. So you got a weather balloon filled with 24.7 liters of helium gas. Okay. In a prep shed. Okay, so that means they're out in some little building, some little shed like on a farm, but they're in the Arctic for this particular problem. Okay. Temperature in the shed is 5 degrees C. Okay, so a little bit above the freezing point of water. It's cold. 5 is cold. That's the refrigerator temperature is usually 4, I think. Right. So the balloon is taken outside, where the temperature is -20. Okay, calculate the new volume. Of the balloon. Okay, so the relationship, the relationship in this equation is that the ratio is constant. So if the temperature goes down, okay, the volume also has to go down, right? Because if you think about it, if you divide by a smaller number, that makes the ratio bigger. So 2 divided by 2 is 1. 2 divided by 1 is 2, right? So the ratio goes up. So they both have to go down to make it a constant. So unlike pressure volume where one goes up, the other one goes down, volume temperature, if one goes up, the other one's got to go up. If one goes down, the other one's got to go down. Okay. And this is all related to how gases behave. We're not talking about the physics of why it does this. We'll talk about that later in the chapter, but for right now, we're just using this equation. Okay, so really you're just going to identify things, and again, make sure your temperature is in Kelvin. So not a bad idea to convert that very early on so you don't make a mistake and leave it in Celsius. So let's draw a little picture. You're inside the shed and you got this balloon and you're filling it, right? Inside the shed, the temperature is 5 degrees C, so it's not too cold. People don't want to be working in too cold. And your volume is 24.7 liters. Then they open the door and they take the balloon out. And now the temperature is -20 degrees C. It got colder, right? Colder is a lower temperature. So if this went down temperature, that means the volume had to go down. So the balloon should be smaller, right? It should be small. Now, I'm not going to claim it's a lot smaller, but it should be at least somewhat smaller, right? I think I exaggerated how much smaller it would be. So let's go through it. So we're going to say our V1 is inside the shed. And our T1, I'm now going to do the conversion. It's the temperature in Celsius plus 273.15, which is 278.15 Kelvin. Okay, for Kelvin. So make sure you do that conversion. And then we'll do outside. So outside, we'll call that V2 and T2. So outside, we don't know what the volume is, but we do know the temperature is -20. So -20 plus 273.15 is 253.15. So notice, you don't ever get negative values for Kelvin. You can have negative for Celsius or Fahrenheit, but not for Kelvin. Okay, so now we got our numbers. Now it's just a matter of doing the algebra. We want to find V2, which is right here. Okay, so let me erase this. Okay, we want to find V2. So I'm going to rewrite this over here. V1 over T1 equals V2 over T2. So we just want to isolate V2. So we need to get T2 to the other side. Just multiply both sides by T2. So V1 over T1 times T2 would be equal to V2, right? You multiply both sides because if you multiply this side by T2, the right side over here, you'd have T2 over T2, which is 1, and that would just cancel, right? So V1, 24.7 liters, over T1, which is 278.15 Kelvin, times T2, which is 253.15 Kelvin. That's going to be your V2. It's not going to be that different. It's probably still going to be around 20 liters or so. So it only went down a little bit, but it went down. 24.7 times 253.15 divided by 278.15. Yeah, you get 22.5. And then your kelvins cancel and you've got liters. Okay, so there's your answer, 22.5 liters. All right. So the key to this is just sort of identifying which is which, making sure that your temperature is in Kelvin, and then the rest should work out. Okay, so let's see. I'll close that. Let's come back. And the last one in this section is Avogadro's law. Avogadro's law says that you're going to take methane gas, and I'm going to write this out, CH4, and it's going to react it with oxygen gas, so that's plus O2, to form water vapor and carbon dioxide gas. Okay, so it's going to form water vapor and carbon dioxide gas. So let's put G's in everywhere. Everything in there is a gas. Vapor means gas. It's not balanced. We've got one carbon on both sides, but we've got 4 hydrogens on the left. So we'll put a 2 here. And then we've got 4 oxygens on the right. So let's put a 2 over here. So now we got a balanced equation. And now here's the question. What volume of carbon dioxide gas would be produced by the reaction if 1.13 centimeters cubed, 1.13 meters cubed of oxygen were consumed? Okay, so this one is actually pretty simple. Avogadro's law essentially says this: the volume of a gas divided by the number of moles of the gas is constant. Okay, so I'll put A for Avogadro. Okay, just so that we know that constant's not the same as it was for Boyle's or for Charles' law. So that ratio is constant. So that actually goes for the entire equation. What you can do is you can say, you have 1 mole here, 2 moles here, 2 moles here, and 1 mole there. That ratio of the volume of the gas to the number of moles is constant. So what you can do is you can say, look, for for oxygen, the volume of the oxygen is given. It's in meters cubed. That's a pretty big volume. That's like a meter by a meter by a meter. Okay. The number of moles of oxygen is 2 moles. Okay. That ratio should be equal to the ratio for carbon dioxide. So the volume of carbon dioxide divided by the moles of carbon dioxide, we don't know what it is for CO2, but we know for CO2 this is 1 mole. Okay, so then you just say, hey, they're equal to each other. Okay, so what I'm going to do is I'm going to say the following. Every time you've got 2 moles of a gas here, you're going to get 1 mole of a gas here. Okay, so it's 1 mole of CO2 for every 2 moles of O2. That is going to be equal to the volume of the CO2 to the volume of the O2. Very simple. So you just take the molar ratio, and that should be equal to the volume ratio. So let's write it that way. The mole ratio is equal to the volume ratio. Okay, so what do we got here? We got volume's O2 is 1.13. So I'm just going to multiply both sides. So I'm going to take 1 mole of CO2 over 2 moles of O2 times 1.13 meters cubed. And that should give you the volume of CO2. So what is that? A half times 1.13. Okay, so it looks like it's point, I guess 3 sig figs, 565. Okay, the moles cancel, so you just got meters cubed. Okay, that's Avogadro's law. Very simple. So all you're doing is you're saying that the mole ratio, so whatever two materials you're considering, whether it be CO2 and O2 or water vapor, and only for gases, water vapor and methane, that molar ratio has got to be equal to the volume ratio. It doesn't matter which one you put on top. Just make sure that if you put moles of O2 on the top here, you would put volume of O2 on the top on the other side, and then you can just solve for it. Okay. The main point of Avogadro's law is that the more moles of gas you have, the larger the volume is going to be. And that kind of makes sense, right? If you put more air into a balloon, the volume of the balloon is going to get larger. Okay. So mole ratio equals volume ratio. All right. And that is Avogadro's law. So that kind of gets us up to the point where we're ready to do the ideal gas law. What we're going to do next tomorrow is we're going to put the ideal gas law together, which comes out of these 3 laws, Boyle's, Charles, and Avogadro. By the way, the one thing I didn't mention with Avogadro is there's an assumption here too, and the assumption is that the pressure is constant. Each of these laws has an assumption that one of the 3 variables is constant. So what we'll do tomorrow is we'll look at problems where they don't have to be constant. We can have a changing pressure, we can have a changing temperature, we can have a changing volume. All 3 of those can be put together into one equation, and that's called the ideal gas law. So we'll look at the ideal gas law tomorrow, and then that's Wednesday. So then on Thursday, we'll look at what's called reactions of reactants and products, of gaseous reactants and products. We'll do that next week. And then we'll probably take all the way through much of next week to finish this up. Okay. Very good. So have a great day. If you have any questions, reach out to me today. And good luck with everything.
Thank you.
Thank you.
Have a good day.
Bye-bye.
Thank you, Professor.
Thank you.